Welcome everyone. This is also assertion reason based type of questions but is depending on the semiconductor. Okay. Let us read what the options are given here. Both A and R are true, but R is the correct explanation of A. That means A is correct, R is correct, and A and R are interconnected in such a way that the second statement R is the explain whatever with the fact given in the statement 1 or as an assertion. B is both A and R are true. R is not the correct explanation of A. That means A is true, capital R is also true. They are not independent but they are interconnected in such a way. Capital A may explain R, but that is not our option. Here you can say A and R are independent. A is true but R is false. That may be an option, that is A is correct but R is completely wrong statement, which is basically does not satisfy any theoretical considerations whatever you have learned. Next is A is false, R is false. That means assertion and reason both are false here. Okay. So let us read what the assertions and reasons are given here. Assertion is the electrical conductivity. Electrical conductivity of a semiconductor increases on doping. So this doping is the word which we need to understood, and electrical conductivity. We basically know these terms when we are discussing the metal. In metal, mainly the free electrons basically conducting, or mainly the free electrons basically taking part in conduction of electrical energy from one place to another place. So if the number of free electrons in a metal increases, the electrical conductivity of that increases. The electrical conductivity of a metal basically denoted as small n E mu, something like that. N is the number of free electrons per unit volume. E is the electrons charge, obviously electronic charge, and mu is the mobility. So if the number of charge carriers will increase, then the electrical conductivity will also increases in case of the metal. So sigma proportional to n. But this is the case of the semiconductor. Semiconductor's conductivity somehow lies in between the conductor and the insulator, but it has one plus point, that if you increase the temperature, semiconductors resistivity decreases, conductivity increases. R versus theta curve, resistance versus temperature curve of a semiconductor, it decreases this. So obviously conductivity increases. Semiconductors are basically made up of silicon. Let us try to understand that silicons, why they are called semiconductors and how they are taking part in electrical conductions. In silicon, all these are basically making a covalent bond. As a silicon having 4 electrons as a valence electron, so its valence is 4, and this is bonds like that. Now what will happen if you increase the temperature? Then what will happen? This electron, maybe initially it have the large value of energy. So by gaining the thermal energy from outside, these electrons is liberated by rupturing this bond. Okay. Then obviously the bond is not here, and the electron comes out from here. So in the place of the electron, we can say here is a absence of the electron, and it is called the hole. Now, due to this rupturing the bond, this electron and hole both are generated, but here this electron is here, but it is bound to this particular silicon atom. Okay, it is not outside, it is not free from here. But due to this increasing energy, due to the direct rupture of the covalent bond, this electron hole pair is generated. Clear? So just try to understand that this way the conductivity of the semiconductor can be increased by increasing the temperature. Now, the word that is introduced there, it is called the doping. Doping is a controlled fusion of the trivalent atoms, may be aluminium, okay, 2 8 3, so it have valence is 3, okay, pentavalent atom, maybe phosphorus, okay, which atomic number is 15, so 2 8 5, valence is 5. So now just try to understand, now in that particular place of silicon, let us consider an aluminium metal is placed here, control fusion, and the ratio of the control fusion is of the order of 10 to the power 6:1. That means in 1 lakh, one trivalent or one pentavalent atom is fused here. So just try to understand that if it is done, then I can replace this silicon. Then I can replace this silicon by one aluminium. Let us replace this. So obviously, if I replace this by aluminium, so aluminium's 3 electrons, basically creating the bonds with this silicon, and with this silicon, these 3 silicons, but with this silicon, it have not created any bond. But there is a space from symmetry in the lattice. This space is completely unfilled. Okay, and this basically serves as the hole. Okay, and hole is, you know that hole is nothing but the absence of the electron. It has the same charge as that of electron, but it is positive. Its mass is same as that of the electron. So a hole is automatically generated without increasing thermal energy within the semiconductor lattice. So electrical conductivity has increased, okay, just by fusing, just by replacing one silicon atom. Now just try to understand, when the temperature is increased, then other silicon bond ruptures and other hole and electrons comes out and taking part in electrical conduction. Okay, so initially by fusing a trivalent atom, the hole concentration is increased. Okay, similarly, if I place here, instead of hole, if I place here a phosphorus, then obviously phosphorus have 5 electrons, so it's 4 electrons, basically creating 4 covalent bonds, but 1 electron left here. Okay, so the electron concentration, by just fusing it has increased. And after that, if you increase the thermal energy, if you increase the temperature, then obviously what will happen? Then obviously the concentration of the electron and hole will increases by rupturing the covalent bonds. Now what concentration I have written here after I have omitted, that is 10 to the power 6:1. It may seem that its value is very less. But let us take 1 mole silicon atom, a lattice made up of 1 mole silicon atom. That means 14 gram silicon. So it contains mainly 10 to the power 23 silicon there. 10 to the power 23 silicon, so in the same ratio it has increased to 10 to the power 7. Please calculate. So within 14 grams silicon, 10 to the power 7 phosphorus is present there. Okay, 10 to the power 17 phosphorus atoms are present there. So just try to increase. If I just replacing in the ratio 10 to the power 6 is to 1, either silicon, either aluminum or phosphorus, trivalent or pentavalent, by creating the p-type or n-type semiconductors, the conductivity is increased by how much? So whatever be the assertion written there, the electrical conductivity of a semiconductor increases on doping. It is correct. Doping always increases the number of electrons in the semiconductor. This thing cannot be said always. Because if you fuse in trivalent impurity, aluminum, we have seen the concentration of the holes increases there initially. If you fuse a phosphorus or pentavalent impurity there, then the concentration of the hole increases, concentration of the electron increases. Sorry. So if you do trivalent, then hole concentration increases initially. If you do pentavalent, the electron concentration increases initially. So the word which is becomes problematic here, it is said always. Always electron, it is not so. So capital A, the assertion is true, but the reason is false here. Capital A is true, but reason is false. So option C is the correct option here. A is true, but R is false. Okay. So we have understood that the conductivity, which is depending on the number of carriers in better way. Okay. It is basically increases on doping, but by doping we can increase the electron and hole both type of carriers by doping either trivalent or pentavalent. Thank you all.